In this video, I'm going to give a brief introduction to significant figures, what they are and why we use them. In the videos following this, we'll talk about what the rules are for significant figures and how to do calculations with them. So for this one, what are significant figures? In essence, significant figures tell you where to round numbers to, whether they be numbers that you record from an experiment or numbers that you write down in a story problem. Either way, you need to know where you should round those digits to. I sometimes find that students will write down every single digit on their calculator just because that's what the calculator spit out. That doesn't mean that your answer should have, let's say, 6 decimal places. So where should you round? That's the purpose of significant figures, to tell you that. Why we use significant figures. Every time something is measured, there is uncertainty in that measurement. Let's say you use an electronic balance that goes to the tenths place, then you can't record an answer or a data point that has a thousandths place in it. So you need to know where you should stop recording your answer to. Every time that you use some sort of a device, the last digit of that numerical number is what we call uncertain, and that's because there's a little bit of rounding involved in that last digit. Even electronically on a balance, the scale may not tell you this, but it's rounding between 0.3 and 0.4. It doesn't tell you exactly where. So that last digit is what we call uncertain. So significant figures tells you how many numbers in your answer you can actually be certain of. So that's why we talk about it here. Next, I'm going to give you 3 quick examples on where you can look at certainty or uncertainty in measurement. The first example I like to talk about is population. If I ask students what the population of Bradenton is, sometimes I'm surprised I get some wildly varying answers. Part of the problem with that is the definition of Bradenton. If you look at Bradenton as, Manatee County or just the metropolitan area, you get one answer. If you look at Bradenton as far as the city of Bradenton, you get a pretty different answer. The city is defined actually a lot more narrowly, and you may not be able to see really closely in this map down here, but it's kind of a narrow strip through Bradenton. But technically, regardless, if you look at Google, the population of Bradenton in 2011 was 50,193. Now, this was in July of 2011. Even given the date, personally, I have a hard time believing there were exactly 50,193 people. I would bet that there's a little bit of uncertainty in this measurement. If I look at that last number, the 3, I think that's kind of tough to say they knew it down to the person. I'm really not even very confident they know down to every 10 people. If someone asked me, knowing this number, what the population of Bradenton was, I would probably say about 50,000. Right? I would round it because I can be pretty darn certain in the 5 number there, in the 10,000 mark. And I have a relative certainty in the 1,000 mark, but I'm not really all that certain about the last few there. So that's kind of a common thing that we do, is we just round numbers to some estimation that we can be fairly confident of. If I took this same population, let's say I told you there were 50,000 people in Bradenton, and I said, a family of 4 just moved to Bradenton. What is now the population of Bradenton? It really wouldn't make any sense if you said there were 50,004 people, right? Because the 50,000 number is pretty terribly rough, that it's an estimated number. So you can't take a number that's very precise and add it to that and come up with an answer and say that this answer is precise down to the ones place. We're going to see examples of that in significant figure calculations, that you can't take a rough number and add it to a very precise number and pretend that your final answer has the precision of your most precise answer. It's actually the opposite. Your answer is going to have the precision of your least precise number that you're dealing with. So that's kind of the way significant figures work. Let's look at another example that's even less mathy. The last 2 are maybe just a little bit silly, but they're kind of fun. My next example has to do with football. It is just about football season, so it's a reason for some of us to get excited and for other of you to hide your heads in the sand because you dislike it so much. But for those of us who like football, I personally am a Nebraska fan, so go Big Red there. One of the things that happens in football is the idea of getting a first down and having the chain gang come out and measure it. If you don't know how this works, here's, so I know some of you guys aren't really into sports. Here's a real simple way to explain it. The football team gets 4 tries to try to make it 10 yards. If on their 4th try they do not make it 10 yards, they have to give up possession of the ball. So here's what happens. On the first 3 downs, the team may make a couple yards or whatever their gain is, and then the referee will take the ball and just kind of eyeball it, maybe stick their foot where the ball was and then put the ball down there to mark the position for the next play. So they do that for the first 3 downs, and they kind of rough out, guess what their the forward progress of the football is at that point. Then suddenly on the 4th down, they pretend that they know really accurately how far they've gone, and this has always kind of cracked me up. Sometimes, if they want to make if they're really close to getting a 4th down to make it to a first down on the 4th down, they'll do what's called a quarterback sneak, where the quarterback will really quickly grab the ball and fall forward as fast as he can, and you get a dog pile. You get all the players piled on top of each other. No one can even see the ball. But the referees always come up, and they dig all the guys off of each other, and down at the bottom of the pile, they'll find the ball. And then, since they know exactly where the ball is, just kidding, they don't have any idea where the ball really is, right? If it's on the bottom of the pile. But they will pretend they do. And then they will take out what's called the chains, and they put one chain that you can't see off this picture here, and they put it where the beginning of the drive was, or where the last first down was. So this would be 0 yards. And then they stretch that chain all the way to the last spot, and at the other chain, that's 10 yards. And so the idea is, if the football is past where this chain is, then you get the first down. And if you don't, then you've failed and you lose possession of the ball. So they stretch the chains out very dramatically, and the referee will put up his hands and say, oh, it was, where it was close or it was far away, or the first down or not. It's very dramatic. But that's kind of an example to me of something that isn't terribly good with certainty. It's always kind of cracked me up. They talk about someday putting technology in the ball. Let's say we put a GPS in the ball, and then you can mark it exactly where it is. Probably won't happen, but it's kind of fun. So that's my second example. My third one is a little quicker, a little less obscure, but I think also relevant. Here's a quick example from track. If you look at the distance around of a track, which I looked it up because I started to second guess myself. Usually tracks are 400 meters, but I did see that that's not always the case. So let's say this is a 400 meter track. Question for you, is it exactly 400 meters? Is it 400 down to what? Down to the nearest meter? Down to the nearest tenth of a meter? Hundredth of a meter? There's got to be some limitation, right? And does it matter? The answer, I would think, would be yes, especially if you're some guy like him, like Usain Bolt, who's trying to break a world record. You need to know exactly how far you're going when you're running against records that come down to 100th of a second. So that's just one other thought I had for you guys on Sig Figs. In the next 2 videos, we'll talk about how you can actually work with Sig Figs as far as numbers go. Hopefully this one helped you understand just a little bit of certainty and uncertainty in measurement.